Have you ever stopped to think about the invisible machines that are just quietly running our digital world, behind everything from your phone to huge
Oh,
networks?
absolutely. There are these fundamental principles working away under the surface.
Exactly. And that's what we're digging into today on the deep dive. We take the sources you give us and pull out the key insights.
Hmm.
We're continuing our computer science and software engineering series looking at automata theory, machines, languages, and computation.
A foundational topic.
Right. Our mission really is to give you a shortcut to understanding this, well, fundamental area. Automata theory, it's the study of abstract machines, right?
Yeah,
And the problems they can solve.
exactly. It connects into theoretical, computer science, logic, even cognitive science in some
And
ways.
the name itself, automata, it's Greek, isn't it? For self-acting?
Yeah, self-acting, self-willed, self-moving captures the idea pretty well.
Okay, let's unpack this then. So when we say automaton, what does that actually, mean in simple terms? Moving past the abstract definition.
Well, think of it as an abstract computing device that sort of runs itself. It takes a sequence of inputs, we often call them words, step by step.
Okay.
And with each input, it jumps between different internal states. How it jumps is decided by its rules, its transition function.
Right.
A really common example is a finite automaton, or FSM. You can picture it like circles for states, arrows for transitions.
Okay, yeah, I can visualize that.
An electronic lock is a perfect everyday example. You type in numbers, right? Each correct digit moves the lock to a new internal state. Get the whole sequence right, it accepts the code and unlocks. Get it wrong, it rejects it.
Simple but powerful.
And that's the really neat part. These automata, they act as finite ways to describe formal languages.
Formal languages,
Yeah.
like programming language.
Exactly like those, yes.
Mm.
Sets of words or strings that follow very specific rules. And what's amazing is that these simple machines can represent infinite languages sometimes.
Infinite. How does that work?
Well, through patterns and repetition defined by the rules.
Hmm.
We usually classify automata by the kinds of languages they can recognize. The Chomsky hierarchy gives a clear structure to this. It maps out the power of different language types and the machines that handle them.
So fundamentally, it's a machine that says yes or no to an input based on rules, recognizing a specific language. I can see the connection to tech now. How did we get this theory, and where's the impact today?
It really got going around the mid-20th century. It sort of spun out of mathematical systems theory, but the unique thing was using abstract algebra to describe these systems.
Abstract algebra. Interesting.
Yeah, and a huge moment was in 1956, the publication of Automata Studies. It had papers from giants like Claude Shannon, von Neumann, Minsky, Kleene. That really cemented it as its own field,
Wow, quite the lineup.
definitely. And today, its relevance is massive. It's core to the theory of computation itself. It's crucial for compiler construction, turning your code into something the computer runs.
Right, the magic behind programming.
Hmm. And it's deep in AI, parsing text, formal verification, proving software is correct. There are even slightly wilder applications.
Oh, like what?
Well, cellular automata, like Conway's Game of Life, they're used in modeling artificial life. And some people even speculate the universe itself might be a kind of giant, discrete automaton just computing its next state.
The universe as a computer. Okay, that's a big idea. A bit mind-bending, honestly.
It is.
Does this mean these machines aren't all the same? Like, are there different levels of power?
Absolutely. The definition is flexible, so you get variations. A big difference lies in their memory.
Memory, like RAM.
Sort of, but more abstractly. For example, a pushdown automaton has stack memory, like a stack of plates, last on, first off. This lets it recognize more complex patterns than a basic finite automaton.
Okay, so memory adds power.
Exactly. And then you have the Turing machine. It uses tape memory, which is like an infinitely long piece of tape it can read and write on. That gives it immense power.
Infinite tape, so it can
Yeah.
do anything.
Theoretically, yes. Anything that can be computed by an algorithm. This leads to a definite hierarchy of powers.
A hierarchy.
Yeah. Different automata types recognize different classes of formal languages. Down at the bottom, you have the less powerful ones, like the deterministic finite automaton, the DFA.
The lock example, maybe?
Pretty much, yeah. And way up at the top is the Turing machine, defining the limits of what we generally think of as computable, which brings up a really key point.
Which I guess is about how these, really elegant, abstract concepts from decades ago are still so central today. We've gone from the basic idea to real-world tech, and now this power hierarchy.
Precisely. What's fascinating is how these abstract mathematical ideas are still the bedrock for understanding what computers can do, and just as importantly, what they can't do.
The limits of computation.
Right. And they're still guiding how we develop everything. Programming languages, sure, but also the very cutting edge of AI. How does this core idea of self-acting machines keep evolving as our tech gets more complex?
That's the ongoing question, isn't it? So next time you use your phone or browse the web, maybe take a second to consider those hidden automata silently working away, shaping your digital experience.